a second-year PhD student working in the NAPHEL group. My work is supervised by Jean-Jacques Greffet and François Marquier, and it's supported by the French Decay and the CNRS. And in this talk, I will discuss the design of highly efficient optical antennas with insights towards fabricability. So first, the concept of antenna can be applied to optical waves in an emission process. When putting an antenna in the near field of an emitter, a small emitter, the size, shape, and materials of the antenna can be designed in such a way that it couples efficiently to propagative waves. And it has applications in bioimaging, in near-field microscopy, or even single photon sources, as I will discuss later. Then, by the reciprocity theorem, this concept can also be applied in a reception-absorption process, where propagative waves will couple efficiently to antennas that will then transfer all the energy into a small absorber. And it has applications in photovoltaic, in photodetection, in nonlinear conversion, or also in bioimaging. In the case of quantum telecommunications and cryptography, one would like to enhance the performances of single photon sources, such as quantum dots or fluorescent molecules. In this talk, those sources are optically excited, though I won't discuss any excitation enhancement. Rather, I will deal with the need to produce a single photon at any willing time, on-demand single photon sources. And to do so, we need an antenna to get a faster spontaneous emission. Then we would like also room temperatures operations. And it means that because of the given usual broad emission spectrum of the quantum emitters, one needs an antenna with broadband operations, which means a low quality factor of the antenna. And finally, one needs to collect all the single photons, and in a naive way, a quantum dot or quantum emitter put alone will emit in any direction, which means that we need a high directivity from the antenna. Let's first address the rate issue. So when computing the average emitted power of a dipole, one can deduce an acceleration of spontaneous emission, an enhancement factor, which is proportional to the imaginary part of the scalar product between the dipole, the electric dipole moment P, with the electric field E at the position of the dipole. And so to understand this equation, let's consider a one-dimension cavity, which is constituted of a perfect mirror and a mirror that can transmit a part of the energy. So a standing wave may exist for some thickness of this cavity. And when putting a dipole at an antinode, at a node of this mode, it cannot couple to this mode. And so this equation tells us that we can inhibit the emission, the spontaneous emission of this dipole. Then, when putting the dipole at an antinode of the mode, one can increase the spontaneous emission. Then, by conservation of the energy stored, by reducing the volume cavity, one can increase the electric field. And so, an increase with the confinement will result in an increase of the emitted power. But there's a limit to this confinement, which is given by the existence of a standing wave, which is half the wavelength. And so to further increase the emitted power, one needs to reduce the loss of the cavity, which means also to increase the number of photons stored. And to do so, one needs to decrease the transmission of the second mirror, which also leads to an increase with the quality factor. And from all those observations, in 1946, Edward Purcell find the exact formula of the enhancement factor of spontaneous emission for a single mode cavity. And this factor is proportional to the product of the cube of the wavelength with the quality factor and with the confinement of the mode. Then for dielectric cavities, because of the standing wave issue, the effective volume of this mode cannot be less than half the wavelength cube. So this leads to a maximum value of the Purcell factor, which is roughly given by the quality factor. So to put some figures, let's see the performances of some fabricated dielectric cavities. So some research groups managed to fabricate fabricable cavities with 2 Bragg mirrors, embedding a quantum dot at the center, and they reached quality factors of several thousands, leading to Purcell factors, which means the fluorescent enhancement, of roughly 30. Then other groups used photonic crystals, with which they reached quality factors of several of 10,000, leading to Purcell factors of nearly 1,000. And finally, to deal with the cavities with ultra high quality factor, there's the case of whispering gallery mode, which stands one-dimension wave propagating in circle, leading to quality factors of 10 billions and Purcell factors of a few thousands, a few 10,000s. For all those beautiful work, there's still a big constraint because of the quality factor that is really high. One needs to put an emitter that has also a very narrow spectral response, spectral emission. And this constraint means that all the work was performed at cryogenic temperatures. So to cope with this issue, one may use plasmonics to further increase the confinement. If one puts a dielectric metal interface in the near field of a dipole, it can excite surface waves called surface plasmon polaritons. So the electric field of a surface plasmon mode decreases exponentially and with a typical length of a few nanometers in the dielectric. And those surface waves have a higher wave vector than the one of propagative modes in the bulk of the dielectric, which means that we need to use some tricks to couple two plasmonic modes. And it works for a dipole close to the interface, because in the near field of the dipole, the near field of the dipole can be seen as a sum of evanescent waves with very high wave vectors. The match of wave vectors can apply. So then, by putting a thin metallic layer on top of the dielectric layer, one can create a highly subwavelength cavity. And furthermore, the usual factor of, quality factor of plasmonic cavities is in the order of 10, which provides broadband operations. So when structuring the metallic layer, using, for instance, the shape of a disk, a plasmonic mode can propagate radially and be reflected by the effective boundaries of the cavity, bouncing over and over. And for some specific diameters of the disk, a standing wave may take place. And so when computing the cross-section electric field, a radial cross-section of the electric field, one finds this standing wave, which is given by a sum of Bessel function because of the cylindrical symmetry. Then this distribution, this electric distribution, will generate a current density in the disk that will radiate to the far field. And moreover, by diffraction, the size of the disk controls the directivity. And we call those cavities the patch antennas. So in collaboration with the Institut des Nanosciences de Paris, with the Laboratoire de Photonique et Nanostructure in Marquier and l'ESPCI, we were able to fabricate and characterize micron-sized patch antennas embedding small clusters of a few 50 quantum dots emitting at 630 nanometers. So numerical simulation of the electric intensity shows the standing wave that I was discussing before. Lifetime measurement using a start-stop setup at the NSP enabled to retrieve an estimation of the Purcell factors, the enhancement of fluorescence, reaching at most 80, and by measuring the radiation pattern, which is in good agreement with the numerical simulations, we show that this antenna provides a good directivity. What?
Can you explain in more detail what is the experiment to measure the lifetime, for example?
The start-stop setup.
Yes.
So you use, okay. So you send, you emit a photon from the source, from the antenna.
How do you excite the source?
Optically. So you send a laser pulse high enough, and then it will produce a single photon.
So it's not the excitation, it's not at the same wavelength?
No. So you produce a single photon, then you send this single photon to, so it's the invariant Twiss experiment. So, not that, oh, what? So you send the, you send this, okay, you excite the antenna. It may produce a single photon, okay? Then you find at what time it has been emitted from the excitation, okay? And then you compute the distribution in delay times of the emitted photons, and you find all those exponential or not exponential decay. Okay, so it's non-exponential because there's a cluster of quantum dots. So each dipoles emit at different times, okay, and have different decay times. And if you fit using a model of the system, you can fit this decay time, and then you find Purcell factors for dipoles oriented perpendicularly or parallel to the patch.
The fact you have several time constants in your, it's not a single exponential.
No.
Interpret this because you have many emitters.
Yes.
But then you can trace also sub-radiant or super-radiant state because you have dipole-dipole interaction between your emitters.
Yeah, this is an experimental method, but this is not his work.
Yeah, yeah,
so
okay.
maybe he's going
Yes,
to talk about something else maybe we can discuss later.
Okay. So then we've got an enhancement factor of 80 and a good directivity. So now let's see if the bandwidth issue is addressed. So one must check that this antenna is indeed broadband. So when computing the fluorescence enhancement with the wavelength, one shows flat responses for all the orientation of the dipole. And it is confirmed with experiments when one measures the spectra of an isolated quantum dot or a cluster coupled to the antenna. So it demonstrates indeed that the antenna is broadband. Now, those antennas were fabricated at the LPN using an optical in situ lithography technique from Pascal Senlar. So first, a 15 nanometer thick silica layer is deposited on top of a gold mirror. Then a solution of colloidal quantum dot is deposited. Then another silica layer and a photoresist are deposited. Using a microscope objective and a dichroic beam splitter, one excites first the quantum dot with a green low power laser and then collect the fluorescence signal. And by scanning nanometers by nanometers the sample, one can map the position of the quantum dots with a 25 nanometer accuracy. And when the beam is centered on a quantum dot or a cluster, one uses the same green laser excitation with high power to expose the photoresist. And the longer the exposition time, the larger the size of the disk exposed. So then we develop the photoresist, leaving a cylindrical hole, and we evaporate a thin layer of gold to fill the hole to generate the disk. And we eventually perform a liftoff of the sample. So one may wonder, where goes the spontaneous emission? It can either decay into propagative mode, either in a plasmonic antenna mode, or into heat. So if, when a dipole is located very close to a metallic interface, say 1 or 2 nanometers away, the field seen by the metal is purely electrostatic. So the absorbed power is proportional to the intensity of the electric field, and the electrostatic amplitudes varies as the inverse cube of the distance to the dipole, which means that if the dipole is too close to the interface, all the emitted power will be absorbed by the metal, and we call this decay channel quenching. So because of this spatial dependence of the electrostatic field, quenching is only dominant for dipoles, metal interface close enough, like 5 nanometers away from the dipole. By putting the dipole 15 nanometers away from the interface, we're avoiding quenching and then only couples to plasmonic modes. So 90% of the decay goes to plasmonic modes, but only 1% will couple efficiently to far field. So to understand such a bad coupling, one may compute the Purcell factor varying with the diameter of the antenna. So for instance, one see a first resonance of the emitted power, which corresponds to the first radial dipolar mode, a second resonance corresponding to the radial quadrupolar mode, etc. And in our case, actually, there's no resonance, and this is due to the fact that the diameter is larger than the propagation length of the plasmonic mode. So there's no radial resonance, and it's equivalent to an infinite patch. And because an infinite patch is flat, there's the mismatch in wave vector that prevents to couple to the far field. So then when computing the radiative efficiency of the antenna, one sees that indeed it couples badly to the far field, only 1%. But this equation, this figures shows also that by going first to smaller resonant dipoles, one can increase the radiative efficiency. And then by changing the wavelength, shifting to the near field, the near infrared, for instance, one can reach higher radiative efficiency. So to improve the radiative efficiency, one can go for smaller resonant patch, get higher emission wavelength, and we choose to use telecom wavelength. And one also needs to scatter the surface plasmonic modes without loss of directivity. So there's two proposed strategies, either a concentric metallic ring grating or the use of a dielectric resonator antenna. So the first strategy is called bullseye antenna, and it has already been studied and fabricated by at least two groups. So for instance, in this case, in the first case, they use it to improve the absorption of a germanium detector placed at the center of the bullseye antenna. And in the second case, it was used in order to have a wavelength-dependent directional emission of the emitters placed at the center of the antenna, which will make for a small spectrometer. So in our case, our approach, we choose to use one patch antenna with one small disk and 3 concentric rings. We performed numerical simulations with a cylindrical aperiodic Fourier model method, and then a global optimization of all the heights and width of the disk and the rings to get the maximum total efficiency. And the total efficiency is defined here as the product of the radiative efficiency with the collection efficiency in a given numerical aperture. And the results are quite good. So we get a fluorescence enhancement of 300, but actually it's also what we would have without the rings. We get a higher radiative efficiency than with the single patch antenna, but not a very high increase. What is striking is the collection efficiency that is really increased, and actually it was quite expected since it's a grating, so it's really directional. And those performances are very broadband. So it's good, but the radiative efficiency is still not really improved. So one needs to go for another strategy. And so there are several groups using a different strategy, using a hybridization with dielectric antennas. So first, in the group of Nicolas Bonneau, they used a metallic dimmer and a high refractive high refractive index dielectric sphere. And in the group of Vaid-Sandogdar, they used two semi-infinite high refractive dielectric media and a small metallic core. And in both cases, they reached radiative efficiency of around 70% and Purcell factors of several thousands. No, theoretically, it's given here.
Where is the emitter?
So in both cases, it's here and here. So you see that there's a lot of geometrical constraints, but that's what was proposed. So in our case, let's consider first an infinite metallic patch. So if the index of the dielectric superstrate is below the one of the dielectric layer, then the plasmonic mode cannot tunnel through the metallic layer, and it barely exists in the superstrate. Then if the dielectric index, refractive index, is the same as the dielectric layer, then the field can, the plasmonic mode can tunnel through the metallic layer, and the field can exist inside the substrate. But because of the wave vector mismatch with propagative modes in the bulk, it cannot couple or weakly couple to propagative modes. However, if the superstrate refractive index is high enough, some propagative modes for some propagative modes, this wave vector mismatch doesn't stand anymore, and then they may couple to plasmonic modes. And when computing the variations of the radiative efficiency with the superstrate refractive index, one sees this exact behavior, and also with a reasonably high enough refractive index, one can go from 0% to 25% radiative efficiency with an infinite patch, which means that by using a structured patch, as the metallic patch proposed, and an infinite or a semi-infinite high refractive index medium, one can reach a higher radiative efficiency. However, semi-infinite high refractive index doesn't exist physically, so one needs to structure also the high refractive index medium. And so what we propose is to use a dielectric cylinder of refractive index 2.58, which corresponds to silicon carbide at 1.55 micron wavelength. Use the same numerical simulation scheme and global optimization of heights and diameters of both the metallic disc and the dielectric cylinder. And to maximize the total efficiency for a numerical aperture of 0.85. Sorry. So the results is this structure, which is which has a 2 micron size cylinder, dielectric cylinder, where you can see that the plasmonic mode couple efficiently to modes of the dielectric resonator. And this dielectric resonator can only radiate lights because it doesn't absorb. And because of the width of the diameter of the cylinder, it's really directional, and so the total efficiency can reach 75%, and this performance is weakly dependent with the off-centering of the dipole, which is suitable for fabrication. And also, it has broadband operations, which is also suitable to work at room temperatures. So now we've got 75% of the emitted power that goes to the far field. And to conclude, we get a spontaneous emission that is enhanced 100 times. 99% of the single photons emitted are collected in a numerical aperture of 0.85. It provides broadband performances, and 75% of the photons, 75% of the emitted power will go into single photons. And all those performances are robust with any deviation with the geometrical parameters, which leads to a possible fabricability. Thank you for your attention.